Y10 angular momentum revisited. In here, I have introduced only a single problem, and actually two problems. The first one is electric dipole moment. A little bit difficult problem. I consider the different mass, a positively charged particle of capital M and negatively charged particle of mass small m. They are separated by distance d, and their direction is making an angle theta. So electric field is along the z-axis, and this dipole has the angle theta. In general, xy plane is in here, and we have introduced the planar radial direction. Here we have a cone. This is a d, and this is a rho vector. That is a rho e to the rho. And there is a tangent direction on the plane, that is a e phi hat. So it has been translated to the center. They are making a right angle. We remember E rho equals cosine phi E1 hat and E2 hat sine phi, and E phi is perpendicular to E rho, that is E1 hat sine phi plus E2 hat cosine phi. The direction of the dipole is along the unit vector n hat, that is making an angle theta with respect to z-axis. Therefore, it has a component along the z-axis cosine theta. Its perpendicular component is sine theta. And among the sine theta component, its x component is a cosine, and its y component is a sine phi. So this is the structure of this problem. Basically, E3 hat dot n hat from this is cosine theta. So everything is ready to solve the problem. First, we have chosen the origin. This origin is at the center of mass. We remember the center of mass is a weighted average of the position vector. We recall that the relative coordinate, usually we wrote r, and in here the relative coordinate is x plus minus x minus, that is the position vector at plus q, and this is the position vector at minus q, and this one has a mass capital M, this guy has a mass small m. Center of mass is a weighted average of the position vector multiplied by their masses and divided by the sum of two masses. Because we have chosen the origin at the center of mass, this one is sum is exactly 0. Because it is 0 in this coordinate system, sum of this is 0, that means that they are opposite. Their opposite means x plus x minus, and the center mass q plus, q minus, and center mass Cm is a point of internal division with the ratio flipped. This mass is capital M, but this distance is proportional to m, small m, and this mass is a small m. However, this distance is they are crossed. So it's a natural capital M multiplied by small m subtracted by the capital M multiplied by small m. It is trivial to find it vanishing. Next, in any two-body problem, total kinetic energy must be a sum of the translational kinetic energy and the rotational kinetic energy about relative to the center of mass. The translational kinetic energy is the kinetic energy of a single particle whose mass is just the sum of the two particles, and the velocity of this term is nothing but the center of mass velocity. So kinetic energy is 1/2 m plus m x dot cm squared is vanishing because we have chosen x cm equals 0. So velocity equals 0 and kinetic energy also vanishes. It's a trivial problem, so it vanishes. The only contribution that remains in the kinetic energy is the rotational kinetic energy, and we know how to deal with this. This is 1/2 mu r dot squared. What is mu? Mu is, what's that? Reduced mass. Small m, capital M, divided by sum. Reduced mass. R dot squared. R dot is actually vector square. It is r dot squared plus r squared theta dot squared. In here, our distance d is actually the same as r. And this d is constant. It is fixed for the dipole, electric dipole problem. So this one again disappears. The only contribution is this one, as r is a d. So we have 1/2 mu d squared and theta dot squared. That's it. This is the total kinetic energy of this system. Let's consider the net force. It's a trivial because the electric field is constant and one guy is a plus q and the other guy is a minus q. So sum of the two forces is trivially 0. So net force is 0. And actually it was expected. We have a center mass system, and a center mass system is an inertial reference frame because this one represents m x cm double dot. This one is x cm double dot equals 0. That means x cm dot equals a constant. However, our frame has x cm equals 0, x dot cm equals also 0. So the center mass will be there forever. Center mass is in an inertial reference frame because of this, and that inertial reference frame is fixed in space. It never moves. Trivial problem. Next, we consider the torque. Torque, the net torque on this system, we have this force to the positively charged particle, this force to the negatively charged particle, and we know x plus, that is this, x minus, that is this, minus minus plus. The signature, both of them are the same. Why don't we sum them up? Denominator, both of them is m plus m. Numerator summed the same. It is a 1. We have d vector, charge q, both of them. So q times d, that is the definition of the electric dipole moment. So the net torque is nothing but P cross E, trivial problem. Now, next, we substitute the P. P is QD. QDN hat. Electric field E0, E3 hat. So let us just make use of P, QD as to be P. So P is here. From here, E0 is here. What's that? This is N hat. That is the unit vector along the electric dipole moment. And we have E3 hat. Cross product. Same thing disappears. E1 cross E3 equals minus E2. E2 cross E3 equals plus E1. Therefore, we have a common factor sign is factored out, and then this E1 becomes a minus E2, and E2 becomes a plus E1. So E1 sine, E2 cosine. Okay, that's fine. So this is factored out, and E2 cosine. Let us pull this negative sign out. In that case, we have E2 minus E2 cosine phi minus E1 sine phi. Now, we know this is E5, that is perpendicular to the planar radius direction, that is E1 cosine plus E2 sine. As a result, our final result for the torque, net torque for the electric dipole is expressed in this way. Now, we find that this is a axis. Where is it? We have a dipole is here. Dipole's planar radial direction projection is this, and the axis of rotation is perpendicular to this. And this one is perpendicular to this planar radial direction, and also perpendicular to the electric field. If we make a rotation about this axis, here we show the negative sign. We know sine theta. In here, theta runs from 0 to pi only. There is no 2 pi. It is only polar angle increases from 0 minimum value to pi only. So sine theta is a positive definite, always a plus. It is always plus. So this one minus E phi is a very important, minus E phi. Minus E phi means if I rotate we always rotate in a counterclockwise sense. However, we have minus E5 means the rotation should be clockwise in this figure. Clockwise means to decrease the angle. Aha! We have this electric dipole P from negative charge from positive charge, and the electric field is this. And we know electric field is this when there is a positively charged plate down there and negatively charged plate. So it is natural to see this positively charged particle will be attracted by these negatively charged particles, and this negatively charged particle inside the dipole will be attracted by the positively charged plate. It is natural to have a dipole has a torque to make its dipole moment aligned, parallel, aligned to the electric field. It is natural. Okay, everything is ready. Next problem. Same situation. Now we have computed torque, that is memorize this formula, but also memorize this formula too. Sine is this PE0 sine theta. This is everything, product is a positive, and it is proportional to minus E phi hat. That means to make this torque is to rotate this dipole aligned to the electric field. That's a very important feature. And then if you know the torque, just like if you know the force, what you need to do is a minus force integral. That is the potential energy. Something like that. The potential energy due to the torque should be done as the same style with the angle. In here, we have a phi angle, theta angle along the direction E phi. So the final result for the potential energy is minus PE0 cosine theta. Here we usually put 0, but in this problem, to make problem simple, we want to kill this unnecessary constant that can be made by choosing minus PE0 as a reference value at angle theta equals 0. What we find is a minus cosine. Let's draw this figure. Usually, cosine is this form, right? From 0 to pi. This is cosine. However, minus cosine is this form. You can see this is a potential energy. Minus cosine, minus cosine, minus cosine. It has the minimum when theta equals 0. It has the maximum when theta equals pi. Okay, potential energy is the lowest. Any force, in here this is torque, this torque is to decrease the potential energy. The torque is tend to make the particle to have a lower potential energy. That's the direction where theta equals 0. What theta is what? Angle between the electric field and dipole. This angle tends to be decreasing due to this torque. It is easy to memorize. However, what you need to do is, as well as you memorize this formula, but you must know the meaning of this formula. So this looks trivial integrals in mathematics class, but mathematics doesn't tell you anything. You need to interpret the physical meaning. So, okay, you find there are 2 points at which derivative of potential becomes 0. When the derivative potential becomes 0, this one is torque is 0. No torque. Here, no torque. Here, no torque. However, here, if there is a perturbation to have E field here and dipole is slightly deviating from the line direction due to the torque, it makes it return to the lowest potential place. So it makes a kind of oscillation. However, if it is opposite, electric field is here and the dipole is opposite, exactly opposite, then it is still there. But if you make a tiny deviation, suddenly it slides down to there. That's a big difference between these 2 equilibrium points. This one is called stable equilibrium point, and this one is called unstable equilibrium point. Understood? These 2. Next, very interesting problem. Now, rotational inertia, actually, I have already told you what the rotational inertia is, and we can repeat the calculation again. Rotational inertia of this two-body system is a mu d squared. And we learned that translation of kinetic energy, oh, that is missing in here. Kinetic energy, this dot squared is 0. So total kinetic energy should be a rotational kinetic energy. There's a 1/2 I theta that squared, and I is a mu d squared, and mu is the reduced mass. We make use of these formulas. We know this is a conservative force. Electrostatic force is a conservative force. So sum of the kinetic energy and potential energy must be independent of time. It must be conserved. Okay, substitute these formulas in here. You end up with this conservation formula. Why don't we take the time derivative of this? What happens? If I take the time derivative of this, we obtain this. We are very familiar with this. Neglect this one, dividing this theta that out, then we can reach the equation of motion, divide mu d squared both sides. Haha, this is identical to the equation of pendulum. That is a G over L previously. Pendulum has the same structure. This scale and this scale is identical to each other, and that is, unfortunately, we have a sine theta that is not exactly to the theta, but if the angle is very small, we can make a Taylor series expansion and neglect the higher order piece. If I want to keep everything together, we need to evaluate the elliptic integral. That solution is already given in the X version. Now it is reduced into a simple harmonic oscillator. And in that case, this frequency is completely determined by the square root of this front factor. Next problem is given in regarding the Bohr model of hydrogen atom. And actually it is known to be wrong. However, by accident, it has first predicted the energy level of hydrogen atom, and that is identical to the measured value. That's the reason why it was famous. However, it is completely wrong. Well, let's consider this problem when, regardless of the fact it is obsolete theory. Bohr assumed that orbital angular momentum of an electron is a bound state of an electron due to the electrostatic force between the proton, and proton is almost 2,000 times heavier than the electron. So center of mass is almost the same as the place where the proton is placed. So electron is assumed to make a circular motion. Ho ho! He thought it is circular motion. Now nobody says electron is making a circular motion. According to quantum mechanics, one cannot predict the exact path of the electron because the uncertainty principle says that both momentum and position cannot be determined simultaneously in an accurate way. But we will learn it later in this semester. Anyway, he assumed that mass of electron, speed, velocity, that is tangent to the radius, multiplied by the radius, that is r cross p magnitude. He assumed that it is a quantized multiple of a reduced Planck constant called h over 2 pi, and this n runs from 1 to 3. So in the beginning, the minimum value of electron's orbital angular momentum is assumed to be 1 multiplied by reduced Planck constant. Later, it was found to be wrong. However, Bohr model of hydrogen atom is based on the classical electrodynamics. Sure, we made use of Coulomb's law and used the Newton's law of motion or second law, and we know how to evaluate the various things in the uniform circular motion. In Bohr's model, the Coulomb's law should be equal to the centripetal force that is made by a massive particle with radius r of the orbit and with the speed v. By making use of the quantization of the orbital angular momentum, we just insert appropriate power for radius and mass to make complete thing L squared. To compensate what has been additionally multiplied, we divide this one by mr squared. You are familiar with this I, rotational inertia. Therefore, this is L squared, and he told us it is h bar n. N runs from 1 to and so on. Using this, we can solve the problem. Radius second power in the third power, radius is completely fixed. And this coefficient is a constant. And we call this a Bohr radius. By accident, this Bohr radius is very, very accurate in comparison with the quantum mechanics. In addition, once the radius is known, we know the Beer theorem. Kinetic energy can be computed. Average kinetic energy, average potential energy can be computed. The sum of them determines the total mechanical energy, and the sum of them is the total mechanical energy that depends on the n squared in the denominator. A fixed value multiplied by 1 over n squared that matches the Rydberg constant that has been measured experimentally without understanding the theoretical background. So his first trial was very successful to reproduce the spectrum of photons emitted from the hydrogen atoms. However, finally, Wolfgang Pauli was able to compute the electron's energy level in the quantum mechanical way. And by accident, the energy levels are equivalent. However, he assumed that angular momentum is determined by the lowest value is n equals 1. He assumed the orbital angular momentum, but the actual ground state of the hydrogen atom does not have orbital angular momentum. Minimum value is principal value is 1, but orbital angular momentum quantum number is 0, that is L0. Anyway, this is a kind of example of angular momentum calculation.